You know, you plug your laptop into the network at the office every day, but have you ever stopped to think about what's really going on under the hood? It's way more than just getting a link light. Today, we're going to tear down a Cisco SD-Access fabric. And I mean really get into it. We're going to trace the packets, step by step, all the way from the moment of connection to actual communication. Let's dive in.
Look, to really understand how this fabric works, there's no better way than to follow one single device through its entire life cycle. We're going to be its shadow, right from the moment it plugs into a port, through all of the security handshakes and address assignments, until it finally gets to talk to another device on the network.
Seriously, think about it. That simple click of an Ethernet cable or connecting to the Wi-Fi, it's an action we do without a second thought. But behind the scenes, there's this incredible automated dance of protocols and policies happening in milliseconds. We're about to pull back the curtain and see exactly how the magic works. Okay, so we're going to break this journey into three main parts. First up, the authentication handshake. This is where the network plays bouncer and decides if our device is even on the guest list. Then, getting an IP address, where it gets its official network ID. And finally, the big one, host-to-host communication, where we see how all this setup pays off. Everything, and I mean everything, starts with security. Before a device can even think about sending a packet, it has to prove who it is. This is the first and honestly, the most important part of getting on the network. And it's all handled by a conversation between the switch it plugs into and the brain of the security operation, the Cisco Identity Services Engine, or ISC. So here's the quick rundown of that whole process. A device connects. The switch immediately calls up ISC and asks, "Hey, is this guy okay?" ISC checks its records, gives a thumbs up or a thumbs down, and if it's a thumbs up, it sends back a whole rulebook that the switch then enforces on that specific port. Simple as that. All right, let's trace the actual flow. It all kicks off the second our endpoint connects to a port on what's called a fabric edge node. Now, this isn't just any open port. It's configured for 802.1x, so it's basically a locked door. The edge node acts as the gatekeeper. The first thing it does is send out a radius access request, a message that goes straight to Cisco ISC. And this is where it gets really cool, because the decision is totally centralized. ISC gets that request and immediately checks against an identity store. This could be its own database, or more likely, something like your company's Active Directory. After validating the credentials, it makes a simple binary choice. It sends back either an access accept, you're in, or an access reject, no way. So, assuming we got the green light, we move from authentication to authorization. ISC doesn't just say yes, it sends back a whole set of instructions. And this is the crucial part. The Fabric Edge node takes those instructions and, on the fly, configures the port. It assigns the right VLAN, and most importantly, it stamps the device with a security group tag, an SGT. Think of the SGT as a digital passport. It defines what that device is allowed to do and talk to, and that tag follows it everywhere it goes in the fabric. So our device is in. It's authenticated, it's authorized, but it's kind of useless. It can't talk to anyone yet because it doesn't have an IP address. So let's get into the next phase, how the fabric handles the good old DHCP process to get our host ready to actually communicate. Now, before we follow the packets, we have to talk about a little hero called DHCP option 82. The easiest way to think about this is like putting a return address on an envelope. In a big fabric, lots of switches might be acting as a DHCP relay. So how does the network know where to send the reply back? Well, option 82 is how the edge switch tucks its own unique address, its routing locator, or RLOC, into the request. It's what makes the whole thing work. Okay, let's watch the request. Our newly authorized endpoint does what it always does. It sends out a broadcast DHCP discover message, basically shouting into the void, "Hello, I need an IP address." The Fabric Edge node hears this shout and immediately intercepts it. It smartly converts that broadcast into a targeted unicast message, injects that critical option 82 info with its own location, and sends it on its way toward the border node. And now for the return trip. The DHCP server, which is probably outside the fabric, sends a reply back. The border node catches it, and here's where option 82 gets its moment to shine. The border node looks inside, finds that RLOC that was tucked in there, and says, "Aha, I know exactly which switch this needs to go to." It then wraps the DHCP response up in a VXLAN packet and sends it zipping across the network directly to the right edge node, which then gives offer to our endpoint. This last step of onboarding, this is the big one. As soon as our endpoint officially has its IP address, the Fabric Edge node sends a registration message straight to the control plane node. It's essentially saying, "Hey, just so you know, The host with this IP and this MAC address, it lives right here at my location. This updates the Fabric's master address book, making our new host officially visible and findable by everyone else. It's the foundation of the Fabric's intelligence.
And there we have it. Our host is officially a citizen of the Fabric. It's been authenticated, it's got an IP, and it's in the directory. So now it's time for the main event, communication. Let's see how the Fabric uses all this groundwork to get a simple packet from our host to another one sitting on a completely different switch.
Now, the whole flow has about 15 tiny little steps, but don't worry, we can boil it down to 3 logical phases to make it easier to follow. First, our source host has to figure out the destination's MAC address. That's ARP. Then, the switch needs to find out where in the world that destination is physically located. That's RLOC discovery. And only then, once all that's sorted, can it start sending the real data. Let's kick it off with ARP. Host 1 wants to talk to host 2, so it sends out an ARP broadcast like it normally would, asking, who has the IP for host 2? Now, in an old-school network, this ARP would flood everywhere, bothering every device. But not here. The edge node intercepts it instantly. Instead of flooding, it sends a precise question to the control plane. And the control plane, which knows everything, just looks it up and replies with host 2's MAC address. No fuss, no muss. And this table right here, this is why the control plane is so powerful. This is its brain. It's just a simple, powerful map that connects who a host is, its IP and MAC address, to where it is in the network, its RLOC. Every single time a device joins, it populates this table. This completely eliminates the need for all that inefficient, noisy broadcast traffic. Okay, so Edge 1 knows host 2's MAC address, but that's like knowing someone's name without knowing their address. It still doesn't know where to send the packet. So it goes back to the control plane with a second question. Okay, where is the device with this MAC address? The control plane does another quick lookup, finds the RLOC for host 2, and sends it back. Now Edge 1 has everything it needs and updates its own local forwarding tables. Let's just stop for a second and really let that sink in. In a traditional network, that first ARP request would have been blasted across the entire VLAN, interrupting every single device, just to find one. In the SD-Access Fabric, that broadcast storm is contained to a single port. The Edge switch's smart query turned a shout into a whisper, a targeted unicast delivery right across the network. It's a massive efficiency gain. And here's what that efficiency looks like in practice. Edge 1 takes the original ARP request from host 1, wraps it up in a VXLAN header pointed directly at Edge 3's location, and sends it across the network. It's just a normal point-to-point packet now. When Edge 3 gets it, it unwraps the packet and delivers the original ARP request right to its locally connected host 2. So to close the loop, host 2 just sends a standard ARP reply back to host 1. Edge 3 wraps it up and sends it back across the Fabric to Edge 1. Now here's the key. Both switches have cached all the info they need. The data path is now built. For this specific conversation, the control plane can take a coffee break. Its job is... And here it is, the payoff for all that prep work. Host 1 sends its actual data, let's say a ping request. Edge 1 doesn't have to think. It already knows exactly where to send it. It wraps the ping in VXLAN, fires it off directly to Edge 3, which unwraps it and delivers it to host 2. The data just flows, seamlessly and efficiently, right across the Fabric. So, if we boil it all down, what have we really seen? The SD-Access Fabric works because it has a centralized control plane that acts as the single source of truth for who and where everyone is. This makes automated host onboarding possible, so security and addressing just happen. It gives us super efficient forwarding because we kill all those old broadcasts, and it enables true policy-driven segmentation where security rules are tied to the user, not the port they happen to plug into. You know, we've just spent all this time geeking out on the intricate mechanics of how the Fabric works. But the really big question this technology leaves us with is this. Now that the network itself can automate the complex how of moving packets, what new applications, what new security policies, what new services, the what, can you finally build on top of it?